All right, so today we'll talk about implication table and I'll explain what that is. But before doing so, just a very quick recap of the last thing we discussed in the last class. Remember, we have been dealing with state graphs and state tables for a while. We noticed that the number of states that you can generate directly links to the number of flip-flops you will need eventually in the hardware. And towards the end of yesterday's lecture, like not yesterday, last day's lecture, we took an approach towards designing state tables from scratch. So we basically started taking every possible states and assigning specific state name A, B, C, D, E, F to it without considering whether some of this could be reused, right? If you remember, we came up with a table, really long table, and then we started checking equivalence. If two rows were equivalent, we used to discard one of them and keep the other. And in doing so, we were able to reduce the total size of the table. And once we get the minimum size table, we converted that into a state graph, and that was it, right? That was more like an optimization approach. So today we'll learn about a similar approach, but it's more, optimized per se, more streamlined, and that is using implication table. And this is basically serving the same purpose, helping you optimize and reduce the number of states required for the sequential logic circuits. All right. By the way, we have almost arrived at the end of the course, and I hope by now you have understood that digital electronics requires a lot of optimization, right? You start with something, and if you don't follow optimization rules, you could just, get any hardware working, that's fine. But remember, we deal with large numbers. And when you're dealing with large numbers, any minor optimization could lead to significant benefit. That's why every time, say, I first showed you how to design a state graph and then how to draw state table from it and design hardware. If you don't remember this on top of your head, hopefully when you revise, it will come to you. But just follow that trend. Like first we learn what to do and what it represents. And then we learn how to make it better, how to optimize it further. So optimization comes afterward. Remember, we learned about designing Boolean logic circuits and Boolean function. We started optimizing Boolean function with algebra, Boolean algebra. And we realized that it's not really manageable as it gets more complicated. So then we went to, remember, K-map. And K-map, felt really nice and smooth and, really manageable until we went up to 5 variable and 6 variable. Then we started seeing, no, we cannot keep doing it. So we basically hit a limit and then we discover something new or invent something new. And then Quine-McCluskey method, I hope you remember that, right? There was a tabular approach that we used after K-map, of course. So using the same trend, we learn about the sequential logic implementation using state graph, state table. We learned about implementing hardware, and then we started learning about how do you optimize this. So today we'll end with that thing. This is basically the final note of optimizing sequential logic. And I hope you remember the reason I'm trying to link between the two is for combinational logic, we started with Boolean optimization, and then we went for K-map, and then we went for Quine-McCluskey. So the larger the system becomes, you need a more structured and manageable and algorithmic approach that the machines can handle rather than human beings. We are quickly going to move over from manual intervention to automatic intervention. So today, the first slide shows you more like a theorem, which is the basis of the approach we will learn today. All right. So trust me, when you look at the theorem, it's mathematical. It feels very complicated and confusing. So I'm not going to go over the theorem right away. Let's first go over the process, and then I'll go back and link the theorem to the process. Does that make sense, folks? All right, so we'll get back to the first slide, which is basically the foundational theorem that determines the approach that we're taking in. Okay, so what is this thing on your left? And this text is for you to read at home later on, right? So, all right, but listen to me very carefully. Hopefully, by the time we are done, it will be easier for you to handle. Okay, so this is a state table. Don't you think? It's a state table. Okay. And we have a bunch of states, present state and next state, and we have some output. Okay. While we are on this, let me clarify a point because I got a question from one of the students about a homework, the bonus homework that I uploaded. And by the way, just a quick side note. If you notice, the size of the homeworks are not the same. If you open, say, homework 2, you see like, there are many questions. Not many, like, I don't know, 8 questions maybe. It's a homework, so you can take the time to work on it. but that has 5%. Just imagine 5% is a big deal. What is the total percentage of your course project? I think 10%, if I'm not wrong. So you see, this is a big advantage if you really want to take use of it. Okay, and the other one has 2% because it's really literally like 2 questions, 1 page. I hope it will take you like 10 minutes to do it. So don't feel like you have to take, if your grades are already good, sure, just leave with it. But I recommend that you cannot predict your final exam grades, can you? And they will not be available until the 9th of December or even later than that, because after you take the exam, it will take me some time to grade them. So better take them. Yes.
You said it'll only take you up to 100, but let's say you had a really like a 97 or something. Is it applied after the final exam?
Yes. That's a good question. So basically, you cannot go over 100. I cannot show you that you got 105 out of 100. So if you are already at 97, maybe you can go up to 100. But if you are at, say, 90, that's a difference between A plus and A, right? It can easily take you over 93% and get you A plus, right? Or A, whatever. Yeah, A and B or the number systems. Okay, any other quick thoughts? Okay, so the reason I took this tangent is in the homework that I uploaded, the optional homework, I deliberately used a different notation because that is also found in some textbooks and some literature, which is in some cases, they don't even show this extra column. They will just show it right after this. Say, for example, okay, just a quick second. What kind of machine is this? Is this milli or Moore? Let me see if you guys can tell me. Is this milli machine or Moore machine? A milli machine, for the milli machine, the output depends not only on the states, but also on the input. Remember? So in the milli machine, you will notice that there will be 2 columns for the output. One corresponding to x equals 0, the other corresponding to x equals 1. Okay? Yes?
It's the one that sequence. It's a million.
Yes, so I know it can be mixed up once in a while. The first one that we learned was milli, and the second one towards the end that I showed you that, hey, the output doesn't depend on the input. That's Moore machine. I know, like, the names are okay, but the point is one of them depends on input as well as the state. The other one, Moore machine, only depends on the state, not the input. Okay, so notice that the output is not showing what happens when you have x equals 0 or x equals 1. You don't have 2 columns showing that. You just have 1 column. That means the output does not care about the input. It only cares about the combination of the states. You see my point? So that's how you can understand this. Now, imagine I gave you a milli machine. So this is a Moore machine, by the way, right? It doesn't depend on the input. So if I gave you a milli machine, you'll have 2 such columns, 0, 1, 1, 0, 0, blah, 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 right? One corresponding to x equals 0, the other one corresponding to x equals 1. So now, in some textbook, they don't separate out this output column from the next state column. Let me show you how they do it. They show it this way: D0, C1, 1, 0, 0, 1. Can anybody guess what it means? So the first element shows the state, which is here as well. After oblique sign, you show the corresponding output. So for x equals 0, this is your next state, this is your corresponding output. Are we good? This is just another way of representing it. I mean, nothing new here, no new concept. Are you good so far? So I deliberately use this notation for the homework so that you get familiarized with it. I didn't want to mix 2 different kinds of notation in the same lecture. So I use this type of notation throughout my lectures. I never use the other one. So in case you are confused. And for this one, since you don't care what x is, you always use the same thing. Even if x equals 0, your output is 0. X equals 1, your output is 0. And 0, 0. And 1, 1. Does that make sense? So you basically copy the same output twice because it doesn't really depend on the input. All right, so let's get back to our track and let's start from the state table. After you get the state table, let's count how many states you have. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 states, okay? And deliberately we have named them in series like A, B, C, D, E, F, G, H. Now, I'm gonna first tell you the approach and then we will go back to the reasoning. So start distributing the states across rows and columns. And there is one thing to remember. Along the rows, you start with the first state and you end with one less. So A, B, C, D, E, F, G. You don't show H. Okay? You don't show H. You don't show the last state. I'm going to tell you why in a second. But do you see what I'm trying to do? Start with the first state, end with one less. Don't show the last state. Okay. Throughout the column, start with the second state. Just get rid of the first state and do everything else. B, C, D, E, F, G, H. Are you good? Okay. And then you create a geometric shape like this, like a chessboard pattern. That's what you create. Okay. And we are going to fill it up soon. But let me tell you one thing. We are trying to see which one of these rows are equivalent. Meaning, if I somehow can show you that state A is basically equivalent to state G. So they are the same somehow. If I could somehow show, then I can get rid of one of the rows. And getting rid of one of the rows reduce a state. And reducing states can lead to reduced flip-flops at some point. Okay, so that is the hope. And that's what we are trying to get to. Now, tell me something. Will state A be equivalent to state A? I mean, do I need to even mention that? State A is state A. It has to be equivalent to itself, right? So the reason why we got rid of this extra row, let me show you. Imagine if you had H. What would, before we get there, sorry, give me 1 second. Okay, let's take one random point here, one random field. And this field represents a pair. And what is that pair? B, F. You see my point here? So what we're trying to do is we're going to pair up different states and we're going to compare them. Are they equivalent or not? Are they equivalent or not? So every point here shows a coordinate kind of situation where you are pairing up different states. Now tell me, now let me show you. So if I drew this H state here, what would be the coordinate for this guy? HH. Okay, how about this? If I started with A, what would be the coordinate for this guy? AA. I mean, does that even make any sense? Like to compare A with A, we know that they're equivalent. I mean, it's not they, it's just one state, right? So that's why we got rid of one here, one here. That's the reason. Okay, all right. So now let's move on to the next slide and show you how to fill out this empty state. So now you have this is called an implication chart. Okay, and we're gonna fill out the implication chart with something. Okay, so you have to really pay attention to this because you see it's gonna get super busy. Okay, so don't miss, don't blink or something like that. All right, so I am going to fill out each and every blocks with a comment. The comment being whether or not they're equivalent or they appear equivalent. So the first thing that we look at is the output. If two rows have the same output, then there is a chance that they can be equivalent. But if the outputs are different, then there is absolutely no chance. Just ignore it. Okay. So I'm not going to do for everything. I'm going to take something randomly. So let's take D, F. Go here, D and F. Do you see that D has an output 0, F has an output 1? Are they equivalent? No. So I'm going to place a cross here. Like they're not equivalent. Let's take another random example. Say B and E. This is, let me clear it up a little bit. Okay, B and E. Okay, so this is your B, this is your E. For B, your output is 0. For E, your output is 1. They're not going to be equivalent. So I'm going to place a cross corresponding to them. Are you good? Can you repeat this for everything? And place crosses where they're not supposed to be equivalent? So that's how you end up with all these cross marks everywhere. Their outputs don't match. But how about the others? Let me show you where they match. Let's start with the first one. First one. You do recognize that this chart, this implication chart, basically represents all possible combinations of all the states, right? You have AB, AC, AD, blah, blah, blah. Everything has to be represented by this. One quick question, and I was expecting, I mean, of course, it's a lot for you to just take in right away. But the question is, why is the chart shaped like a triangle? Why it is not like this, like a square, for example, right? And I'll give you the reason. So above the diagonal, so imagine if you have, say, A, G here, above the diagonal, there will be a point which will be GA.
Yeah.
Mirror. You see my point here? So if you have 1, 2, there will be 2, 1. 3, 4, there will be 4, 3. But all we're trying to do is you're trying to compare two. Does it change anything to compare A with B versus B with A? It's basically the same. So why would we even try to repeat the same thing twice? So we are getting rid of the top half of the diagonal. Okay, that's why it is shaped like a triangle. Are you good? In case you had that question at home. All right, now the first point here is AB. Let's see. Let me just zoom in a little bit here. This is your A, this is your B. Notice their outputs match. I'm not going to say they're equivalent. I cannot say that they're equivalent. You know why? Because the next states don't match. Are you still with me? But you don't know whether these states are equivalent. There is a possibility that state D is basically same as state F. There is a possibility that state C is basically equivalent to state H. We don't know. That's what we are trying to find out, right? In case that is the case, if that happens to be the case, then I can say A and B are equivalent. Can I say that? Can I mean, in case, let me repeat that point again. I see that out. First thing is if the outputs don't match, no way that they're going to be equivalent. Just ignore them and cross it out. But if the outputs match, like here in this section, A and B, you cannot definitively say that they are going to be equivalent, but you can say that they will be equivalent given that this corresponding states, D and F are equivalent and C or H are equivalent. If they are equivalent, they are the same, then I can say A and B are equivalent. Are you good so far? Are you okay with it? Or okay, so that means I'm going to add a condition that, hey, at this point, you can have A and B equivalent if, let me show you, instead of showing this D equivalent F, which is difficult to type, we basically just show DF and CH. We just show a pair. DF should be the same, CH should be the same. Does that make sense? And the full form is shown here. A is equivalent to B if, you know what if with two F's represent, right? If and only if. There are no other way. That D and F are same, C and H are same. Is that difficult? Be honest, right? Okay. Trust me, many things in engineering and science appear to be more complicated than they are. So honestly, it's a very simple argument. You can try to explain this to your cousin, right? Hey, when will two things be equal? When every component are the same, right? So these things will be equal when their components are the same. Okay. Let me take you one more example, show you one more example. Okay. So can anybody pick one combination for me? Just a random, just throw something out. Anyone? Which one? AD. Okay. Thank you. So A and D. Let's see. AD. Let's try to make sense of it. You have A and D. First, let's check whether their outputs match. They do. But notice the next states don't already match. So can I say that they will be equivalent when D and A are equivalent and C and E are equivalent? Can I say that? Can I say that? Basically, when do you think this A and D will be equivalent? When every corresponding state, D and A are equivalent and C and E are equivalent. Okay, so I'm going to say, don't worry about this cross for now. Okay, I haven't even gone there yet. So you are just going to write D and A and D are the same. So A and D are equivalent and C and E are equivalent. That's the condition. Do you guys agree with it? Okay, one last example before we move on. I'll let someone else speak. Can someone pick a combination? Please. Please. What did I tell you about speaking up? In real life, Whoever speaks up get the promotion. I mean, you cannot just speak up once and get a promotion. You'll have to continue speaking up. So develop that habit. Yes. F and H. Okay, thank you. You got a promotion. F and H. F and H. So this is the one. Let's do it. Let's first go back here. F and H. First, see if their outputs are the same. Yes, they're the same. But how can I ensure that they will be equivalent? By pairing up C and F and B and G. So let's see. C and F and B and G. Are you good? So can you now populate the entire table? Do you have the confidence to do so? Are you good? Okay. So this is the fast pass. Basically, we have just gone through this once. That's why it's called the fast pass. Okay. Are you good so far? Okay. Now, we're going to do something additional to this table that we have created. So hear me out. Now I'm going to explain why. Notice that there are two things that were crossed out. See, everything else is fine. Just two things were crossed out deliberately. Okay. And what are these? Notice something. What is the combination? A and D. And AD showed up in the combination. Okay. And how about this one? This is C and E. And C, let me erase this. This was CE, and the combination is also CE. This was AD, and the combination is also AD. So basically, it's similar to saying A and D will be equivalent if A and D are equivalent. You see my point here? This is repetition. Basically, you don't even need to consider that. And by the way, this is mentioned here. This is called self-implied pairs. Okay, this type of situations are called self-implied pair. Like, I'm going to be first if I am first. Like, they're repeating the same thing. So A and D are equivalent, given that A and D are equivalent, and something else. But you don't have to mention that. It's already understood. So that's why we got rid of these two repetition. That's the reason. Okay. After you get rid of this, what you get is, why is it? Yeah, this one. You get this one. This is your actual first pass after getting rid of those self-implied pairs. So we are here right now. Are we all together on this? Anyone lost? Okay. Now we will go over this implication chart one more time. And you have to pay real attention to it now, because otherwise you'll miss. I'm going to zoom in to it. And trust me, you cannot understand this by reading through the paragraph. You'll probably get more confused. I get confused when I try to read the paragraph. I say, okay, I'm just going to put it out there for you to read and judge for yourself. Okay. Anyways, yes. Sure. Yes. So that's a good question. First of all, notice only this one is repeated, but the other one is important, right? If I get rid of the box itself, then I get rid of both combinations. But you're not saying it's wrong. You're saying that it is already implied by saying that A and D will be equivalent when, say, literally, I'm just spelling it out. Yeah. You mean about this one or a different one?
A and C.
Okay, A and C.
Same combination. Or, yeah, C.
A and C. I don't think there is any repetition here. E, C and E. Okay, let me show you. So C and E. Okay, let's see. What about C and E?
You have the same box as the other one, as A and D.
Oh, right. I see what you mean. Okay. So the question is, first of all, notice, this is ADCE, this is CEAD. But that's a good point, by the way. Individual boxes, they don't talk to each other because the combination that they're representing are different. That's how we chose it this way, so that there is no repeated combination. Okay. But internally, they can be the same. And interestingly, you got the right one. They are hinting at equivalent states already. You will see after we go through everything, you'll probably identify these two fields and show they are equivalent. Okay, so you already got it. This is a great point. This is the power of manual, intervention. However, just for a second, imagine if you had 512 states and 512 states, how many can you think you can manually track, right? It is impossible. And instead of having 2 rows like this, you have multiple rows. So there you go. It can easy, when you deal with these small scale problems, it often feels like, okay, we can manage it. But the key point is getting to computers and really large systems. Okay, very good point. Thank you. Okay, so this one, ready to pay attention? You have to. All right. Now, notice there is a cross here. It was good in the previous figure. Right here, it was okay. All on a sudden, we just crossed it out. Why? I'm going to show you why. Okay, so now we will look inside the box and show the pairs and see the pairs. The first one is DH. What is D? This is D. This, where is H? Basically, we'll have to take D from here and where is H? H from here. So this is your DH. Are you good? So I'm looking for DH. What's there in the DH box? Cross. That means DH cannot be equivalent. It is showing you DH cannot be equivalent. So I'm asking, hey, A and B will be equivalent if, sorry, I misread it. This is not DH, this is DF. Are you, don't get confused, okay? I was misreading it. This is D and F. Let's go back. So D and F, same thing actually. So notice the box corresponding to DF shows a cross. That means D and F cannot be equivalent. And I was saying that, hey, A and B will be equivalent if D and F are equivalent and C and H are equivalent. But, and by the way, both of them have to be equivalent. But one of them is not equivalent already. So what do? You say that, hey, there is no chance this is gonna work. You just cross it out. You can check both or one. Even if one of them is crossed out, the entire box is crossed out. Because it is AND. You need both of them to work. Okay, are you good? Okay, let's do one more example here. Let's take this one. Okay, what is inside this box? EF. Where is E? Where is F? Okay, I basically went ahead of myself. This is a little bit more complicated case. I'm going to show you something simpler and then we'll get to this complicated stage. It is okay, but I'm going to show you something a little bit less complicated first. Yeah, I think this is something we can take. So let's take this one, BF. This is B, this is F. What is the box corresponding to BF? Cross. So I'm going to cross it out. So can you go over this entire thing, take one box at a time and see whether they can be crossed out? Okay, I think we better start from here. That way it is easier for you to see. Okay, how about AF, EH? What is AF? This is A, this is F. Crossed out. So cross it out. Can you do it at home? Okay. One more time, one last time. This is an example. CF, where is C? This is C, this is F. Okay, I don't know, because there is something here. I don't know. It's not crossed out, is it? If it is not crossed out, I'm not going to cross it out. Are you good? So that's what we ran into in the previous example that I was going to give. It is not crossed out yet. So I cannot say that this is crossed out or not. This is still going to be valid. I'm going to cross it. I'm not going to cross it out. Okay, how about a different example? Say this one. CF again, which I cannot cross out. But how about BG? If you cannot cross out the first one, look at the second one. What is BG? B and G. Hey, oh no, that's also not crossed out, is it? B and G, not crossed out. So I cannot cross out this one as of now. Are you still with me? So cross out the ones you can. And wherever you don't see a cross corresponding to it, don't cross it out. Just stop. Just stop. Keep them as is. You know what to do now? So take every one of these combinations, look for whether or not you can cross out either of them. You can cross either of them, you can cross the entire box. And after you go through this pass, this is first pass, you basically cross out the ones you can. Are you okay so far? All right. Now, let me show you one thing here. Okay, let's move to the next. Yeah, this is where we have the second pass. So this is what you get after crossing out those sections. Okay, so this is what we got after the first pass. Notice this is cross, this is cross. I'm gonna make them prominent so that they're visible. Cross, 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 cross. They're prominent now. So notice you have already simplified this graph significantly. Almost everything is gone. You see, except for a few here and there, except for a few here and there. And by the way, after you go through one pass, based on whatever is already available, and whenever there is a confusion, you just keep them. You don't change them. Okay, so you create a new version. So this is our new version. And after you have that version, you go over them one more time. So basically you keep repeating it. It's like a loop. Okay, now I'm going to show you. Let's change the color. Say, let's take this, AG. Okay, let's see what happened here. A and G. Uh-oh. Is it crossed out? Not yet. Okay, how about, let me show you. How about this one? How about this one? AD. Where is A? This is A, this is D. It's not crossed out yet. Let me show you one more thing. How about this one? CE. This is C, this is E. Notice it is also not crossed out. You see that? So basically, you keep doing it over and over. Like, let me go back again. So you do it once here. You cross out the ones that you can cross out, and you create a new version. And then, give me a second. Yeah. And then you go over this one more time, and you cross over the ones that you can cross out. Okay. After that, if you see that there is something that you couldn't cross out, okay, somehow you couldn't cross it out. One thing that I'm going to show you now is this one. Notice AG. Do you see that AG was crossed out eventually? Why is that? Now we cannot cross out anything new, but I'm going to take a deeper dive into AG. AG shows A and G, which has two other things inside, which is BD and CH. Where is BD, folks? This is B, this is D. Uh-oh, that is crossed out. So you are getting deeper into it now. Are you still with me? All you're trying to do is basically following the trail. That's all. So let me take a step back. I'm going to assess whether AG can be equivalent. Okay. AG corresponding to this one, A and G. And that has two conditions inside it. I don't have a cross here. So I have to go deeper into it. So let's see. BD. Where is BD? This is B, this is D. And it has been crossed out in the previous stage. Even if you get one of them crossed out, the entire thing will be crossed out. You cannot have anything crossed out. Are you with me so far? So what I'm telling you is first cross out the ones that are easy. Okay, then set it aside. Do one more sweep and cross out the ones you can. And then finally, when you're stuck and you see that you have to compare this one with other ones, then you go deeper into them. You go deeper later on. Don't go deeper initially. Then it will be very confusing. Okay. And you go deeper and you see whether or not this could be crossed out eventually. So finally, this one was crossed out. Let me show you one more example which couldn't be crossed out. Like say AD. Let's see. Where is AD? A and D. Oh, okay. AD has CE. Where is CE? C and E. That is also not crossed out. So if you go deeper, none of these are crossed out. So you're good. So this one will stay. Sorry, AD will stay. Are you okay with me so far? So when we just, okay, I'll deal with it later. Let it be, let it be, let it be. And finally, when you have dealt with everything else, you saw how many crosses were there. Only 3 remained. And then you take a deeper dive into all those 3 combinations. And eventually you're able to cross out one more of the 3. And then only 2 remained. And this is basically where you stop. And if you go over one more pass, nothing will change. And the point is nothing changed. You compare whether anything changed or not. If nothing changes, that's where you stop. And if you're feeling like, hey, I mean, this is overwhelming. For you, it is overwhelming. For a computer, it is 10 millisecond. Okay? Yes.
Is it always two remaining or?
No, not always to remain. That's a good point. Again, by the way, that depends on the size of the overall, thing, and also depends on how these are distributed. I can design them in a way that multiple will be equivalent. All right. So this is just a random example where two happen to be equivalent, and I haven't showed you which ones are equivalent, by the way. But are you good so far with this second pass? First, tell me that. Okay. All right. So please read them at home. Okay, so these two are our conclusion. Don't look at, first of all, don't look at what's inside. That doesn't matter. This is a confusing situation. And this is taken from from the textbook. This example is taken from the textbook. So I had less control over it. And it is very difficult to predict which one will give you what I'm looking for, actually, because it's so complicated and so many steps. But I'm going to tell you here, don't look at the combinations inside it. You just use them to show that they couldn't be crossed out. Look at the coordinates. What? So it's not, let me show you. Just erase this thing out. Erase this. But these two squares represent two combinations. Which combinations do they represent? Can anybody tell me? AD and CE. These combinations should be something that you care about. So what I'm saying is A and D are equivalent. So A and D are equivalent. And I'm also going to say that C and E are equivalent. I mean, you see the source of the confusion here? Because inside you also had AD and CE, basically. So it's a coincidence. It doesn't have to happen, by the way. Are you okay with it so far? And it is mentioned. Please read it. And I mentioned that here in the text as well. But I'm also highlighting that make sure don't look at what's inside. This is only used to not cross out things. Whichever is not crossed out, look at the combination for that. A and D are equivalent and C and E are equivalent. You learn that from all these steps. So when I say A and D are equivalent, can I replace D with A? Keep the one that comes before and replace the other one. Can I replace D with A? And I told you C and E are equivalent. Can I replace E with C? Okay, so this was your original state table. And this is your reduced state table. Notice what's missing. Where is D? What is D? I replaced it. I don't need it because it is repeated. If you have A, you have D. Just cancel this row out. Okay. How about E? Where is E here? There is no E because I crossed out E. As long as you have C and A here, it's basically the same as D and E. So I'm going to cross out these two rows. First, you could reduce two rows by going through these steps, but that's not the end. Also take a deeper dive. Hey, there is D here, but here you don't see D anymore. What do you see? A, because I replaced D with A. Okay, one more example. E, right? Instead of E, I'm going to use C because basically wherever you see D and E, you replace them with A and C. That's all. Are you good so far? And that's how you can reduce the size of the table and make it simpler. Do you understand the steps now? And remember, the power of this approach will be apparent when you have many states. Instead of like 8, if you have 800 or 8,000 versus 8,000, your computer will still do the same. But you cannot manually do it anymore. It's like literally beyond ourselves. All right. So now what I showed you, hey, remember when I showed you that these two states are going to be equivalent when these internal states are equivalent? This argument is mathematically expressed here. If you want, you can read it, but you don't really have to. This is like a theorem, mathematical theorem, that these two states are equivalent, given that their internal states are equivalent. That's all. Okay. All right. So that's quickly finishing up that one. This is the last slide. And I decided to mention it later because it sounds so scary. All of these that you have learned so far, Millie machine, Moore machine, all this state diagram that you have done, they're typically discussed under a section called FSM, finite state machine. And I'll explain the reason behind this name. And there is another name by that people sometimes use called automaton. It's basically any machine that follows a rule automatically, right? There is a rule that you set and the machine follows it. That's called an automaton. But what is finite state machine? First of all, you now understand what states are. Basically, a flip-flop has two states, 0 and 1 in the output. Now, if you have a register with, please try to answer this. If you have two flip-flops in a register, how many total states do you have? Thank you. Thank you. Yes, you can have 0, 0, 0, 1, 1, 0, 1, 1. So you have 4 states. And basically, that's what states is. States, with 2 flip-flops, you have 4 states. With 3 flip-flops, you have 8 states. So you understand by now what states are, I think. Why are we mentioning it as finite? Okay. Can you definitively tell me how many states will be there with 4 flip-flop? Yes, 2, 2, 2, 2, 2 raised to 4. You can easily tell me how many, and this is always finite. There is a number. You cannot have infinite number of states, for sure. That's why it's a finite state. And machine is basically a mechanism that follows a rule. For example, this machines, doesn't matter whether milli or Moore, as long as they're based on flip-flop, this is one interesting rule that they follow. They either follow the rising edge of the clock or falling edge of the clock. So there is a rule that they follow. Okay, so this is a machine essentially. So that's why the name finite state machine. You're dealing with finite number of states in a machine. That's a mouthful, but this is what you have dealt with so far. You have already covered FSM, finite state machine. Okay. Okay, so that's the end of our technical discussion. Thankfully, we were able to finish on time. And I knew that because it's not much. It's typically easier. But you know the drill. If you don't practice at home, this will be all blank at some point. Okay, and please follow along. And that's why you have the recorded video, I hope. If you forget, you don't even have to. I highly recommend, don't even try to read the text. I mean, it's so confusing. It's taken completely from the textbook. I didn't write it. But follow the instructions and do it yourself with pen and paper. Hopefully you'll be fine. All right. So with that, we'll stop here today. I will go, like I said, on Monday, we'll go over the concluding remarks and some high-level overview of the course. If you can make it in person, great. If you cannot, what I will do is I'll share the Zoom link beforehand so that you could join live, because you might have questions that you want to ask live. Okay, so that way we will be able to handle it well. Thank you. And your midterm scripts are with me. Please collect